All right, whenever.
So we are happy to have Giacchini in our seminar today, and he will talk on asymptotic packing of geometric graphs.
Okay, thank you, Shira, for the introduction, and thank you all for coming. Today, I will talk about on asymptotic packing of geometric graphs. This is John work with Daniel Cranston, my advisor, Jacques Westrada, and Alexandra Veselek. And we also want to thank Abdel Basit, Austin Aid, and Bernard and Shira for helpful discussions on this problem in GRWC 2021. Let's first introduce some history for graph decomposition. Let H be a graph and G be a smaller graph. Then we say H has a G decomposition if it can be decomposed into H disjoint copies of G. A C3 decomposition of Kn is usually known as a Steiner triple system. The figures here show a Steiner triple system of size 7, and it is also usually known as the Fano plane. And it is well known that a Steiner triple system exists if and only if n is equivalent to 1 or 3 modulo 6. And for graph decomposition problems, Wilson in 1976 basically completely solved it. He proved that for an arbitrary graph G, Kn has a G decomposition if n is large enough and satisfies certain divisibility conditions. Okay, and in general, the graph decomposition is hard and...
Sorry, what's the GCD of a graph?
Okay, the first condition means that the number of edges divides and choose 2, and GCD, the second condition, the GCD of a graph G is the GCD of its degree.
Okay, cool.
Degree of the vertices.
Makes sense. Great, thanks.
Yeah, obviously, this should also, it's also a necessary condition for it to be decomposable. Okay, and basically, this solved all the problems for graph decomposition. And now we will introduce a slightly easier questions that is about graph packing. A G packing of H is a collection of H disjoint subgraphs of H that are isomorphic to G. We let P of H and G be the maximum size of a G packing of H. Then clearly, P of H and G is at most the number of edges in H over the number of edges in G. And further, we say a graph G is packable if it satisfies the following equations. The numerator of this fraction means the number of edges covered by a maximum G packing, and the denominator of this fraction just the number of edges in the complete graph. So basically, a graph is packable means that there exists a G packing of Kn that covers all but little o n square edges. And it is not hard to see that any arbitrary graph is packable by Wilson's theorem because the trick is that basically the Wilson theorem says when n is large enough and falls into some modulo class, then you can find a perfect packing or a decomposition. So, and under this definition, we can always ignore some constant number of vertices. And by doing that, we are only losing big O(n) of edges. Okay, so basically all graph packing problem will be solved by Wilson's theorem. Now let's consider a variant of the graph packing problems, that is the geometric graph packing. A geometric graph G is a graph whose vertices are in general positions in the Euclidean plane and whose edges are closed line segments. So basically, they are just straight line drawing of graphs on the plane. And we say two geometric graphs are congruent to each other if one can be transformed into the other by translation and or a rotation. And we say a geometric graph is plane if no two of its edges cross. Here is some examples of geometric graphs. And for any abstract planar graph G, we let P of G to denote the set of all plane geometric drawings of G. And moreover, we let P star of G be the set of plane geometric drawings of G whose vertices are in convex positions. So under these notations, if we let C4 to be the fourth cycle, then G1 is not contained in P of C4 because G1 has a crossing. And G2 is contained in P star of C4 because it is plane and all of its vertices are in convex position. And G3 is in P of C4, but not in P star of C4 because it is plane, but its vertices are not in convex position. Okay, now let's introduce the definition of geometric graph packing. Let H be a geometric graph and let G be a set of geometric graphs that all have the same number of edges and which denoted by U of G. We say a G packing of H is a collection of edge disjoint subgraphs of H that are each congruent to some member of G, and we let P of H and G be the maximum size of the G packing in H. And similarly, now we let Dn to be a sequence of geometric drawing of the complete graph such that Dn has n vertices. Now we say that Dn can be asymptotically packed by G if it satisfies the following equation. Basically, it is saying that it is asymptotically packed by G if a maximum G packing covered all but little O(n) squared edges of Dn. Okay, and G, we say G is geometric packable if any geometric drawing of the complete graph can be asymptotically packed by G. So finally, we are ready to show our results. We have shown that if G is a planar Hamiltonian graph, by Hamiltonian, we mean that a graph that contains a Hamiltonian cycle. If G is a planar Hamiltonian graph, then P of G, that is all the plane copies of G, is not geometric packable unless G is one of C3, C4, and theta 1, theta 2, theta 3, theta 4 in the figure below. And further, P of G is geometric packable if G is one of C3, C4, and theta 1. So in other words, we have shown that when G is all but at most 6, for all but at most 6 planar Hamiltonian graph, P of G is not geometric packable. And we have shown that 3 among the 6 is geometric packable. So we still have 3 of them open. The geometric problem for P of G when G is one of these 3 are still open, and we conjecture that they are geometric packable. And the reason is that, in fact, we can show that they are packable when the complete graph has vertices on strictly convex positions, which we will show later. Okay, here is our second results. If we restrict the subgraph we can use to be not only plane, but also convex, then we can show that if G is a planar Hamiltonian graph, then then P star of G is not geometric packable unless G is the triangle C3. And we know that P star of C3 is geometric packable. This is because the existence of Steiner triple system. Okay, now let me show you the proof that P of C4 and P of theta 1 are geometric packable. First, to prove that P of C4 is geometric packable, we let Dn be an arbitrary geometric drawing of the complete graph Kn with vertices V1, V2 up to Vn. Without loss of generality, we can assume that V1 is on a convex hull and that V2 up to Vn appear clockwise order around V1 with edges V1, V2, and V1, Vn on the convex hull, as shown in the figures here. And with this notation, now we picked all the 4 cycles of this form. Don't bother to read those. Let's look at the figures here. So basically, the idea is that the straight line determined by V1 and V5 will partition the plane into 2 parts such that each part contains equals number of vertices. So we can pair these vertices up, and each pair of vertices will form a C4 with V1 and V5. So we pick all those planes C4 and add them all to our packing. And not hard to see that this C4 will cover almost all the edges incident to V1 to V5, missing at most 3 of them. Okay, so the next step is we delete V1 and V5. Then we will have a drawing of Kn-2, and then we continue recursively until the drawing has at most 3 vertices. So the next round, we may pick V2 and V6 and partition the plane into 2 parts. And then we pair the vertices on both parts up and then pick the plane C4 that covered almost all edges incident to V2 and V6. And then we delete V2 and V6. And then now we look at V3 and V4. So we continue recursively until we have at most 3 vertices left. Okay, so each time we deleted vertices, we discard at most 3 uncovered incident edges. Thus, the resulting packing recovers all, but at most big O and edges of Dn. So this completes the proof that planes C4 are geometric packable. Okay, now let me show you why P of theta 1 is geometric packable. This is a little bit trickier than P of C4. Again, we let Dn be an arbitrary geometric drawing.
Can you remind us what is theta 1?
Okay, yes, theta 1 is C4 with a chord.
Okay, sounds good.
So P of theta 1 are all plane copies of C4 with a chord. Now we want to show that P of theta 1 is geometric packable. We let Dn be an arbitrary geometric drawing of the complete graph Kn, and we let M to be the floor of N over 4. Okay, the trick is that by Ham-Sandwich theorem, there exist 2 straight lines partitioning the plane into 4 parts, P1, P2, P3, and P4 in clockwise order. Like this, we can always find two straight lines on the plane that partition it into 4 parts, each part containing at least the floor of n over 4 vertices. We denote these vertices by V sub ij, where I is from 1 to 4 and j from 1 to n. And then after this, we pick all the plane θ1 of this form. And what's important of the plane θ1 of this form is that all 4 vertices are from different parts of the plane. And the chord has vertices. The chord has vertices on part 1, P1 and P3. And it is not hard to check that a θ1 with this property is always plane. And so they are plane, and we also want to show that they are all disjoint. If we look at the figure on the left-hand side, and when we fix k equals 1 and vary j from 1 to n, then those plane θ1 in colors will be the plane θ1 that we picked. And we can check that, in fact, this plane θ1 will cover all the edges between P1, P2, P2, P3, P3, P4, P4, P1, and P1, P3. Basically, it means that this plane θ1 will cover a blow up of the θ1. Okay, and it covers the blow up of a plane θ1, almost all edges of the blow up of this plane θ1, but at most 3 n edges. And what remains to be covered now are 3 complete subgraphs, one induced by vertices in the union of P2 and P4, and the others induced by vertices in P1 and vertices in P3. And we can cover them by induction. And more formally, we try to prove that we can cover all but f of n equals 2 times n times log sub 2 of n edges. And the induction proof goes like this. And we have shown that first we cover the blow up of the θ1. And in this step, we miss at most 3 n edges. And then we cover the remaining 3 clicks by inductions. And in these steps, we miss at most f of n over 2 plus 2 times f of n over 4. And due to the forms of f of n, this sum, in fact, equals exactly f of n. So this completes the induction proof. So for plane θ1, we can cover all but big O n times log n edges. Okay, so we have finished the proof. We have finished the proof of the positive part of theorem 1. And now in the remaining of this talk, I will show you the negative part of theorem 1. And the proof for the negative part of theorem 1 use the notions of convex geometric graph. A convex geometric graph, or CGG for short, is a geometric graph whose vertices are in convex position. And two CGGs are convex isomorphic if some graph isomorphism between them preserves the cyclic order of all vertices. Given two CGGs G and H, a G packing of H is a collection of edge disjoint subgraphs of H that are convex isomorphic to G. We let P of H and G be the maximum size of the G packing in H. And we say a CGG is plane if no two of its edges cross. Okay, now we let this Cayley K of n be the complete CGG on n vertices. A CGG G is convex packable if it satisfies the following equation. It basically means that a maximum G packing of this Cayley Kn covers all but at most little o n square edges. And clearly, for any planar Hamiltonian graph G, there is at most one way to draw G as a plane CGG. This is because a Hamiltonian graph G, it contains a Hamiltonian cycle. And there is only one way to draw a cycle in a convex and plane way on the plane. So there is at most one way to draw it as a CGG. Therefore, if P of G is geometric packable, which means that it can pack the complete graph where all the vertices are in convex position. And this implies that G as a plane CGG is convex packable. So in other words, it means that if we can prove that G as a plane CGG is not convex packable, then it would imply that P of G is not geometric packable. And that's how we prove the negative part of theorem 1. And we let this Cayley K denote the convex plane K cycles. And here is our third theorem. We have proved that for all plane Hamiltonian CGGs, all plane Hamiltonian CGGs are not convex packable, except for 6 of them. That is the 2 plane cycles C3 and C4, and the 4 CGGs theta 1, theta 2, theta 3, and theta 4. And in contrast to theorem 1, here, in fact, we can show that all 6 of them are convex packable. So that's why we conjecture that the remaining 3, theta 2, theta 3, and theta 4, might also be geometric packable. Okay, let me show you the negative part of this theorem, which would also imply the negative part of theorem 1. Before doing that, let me introduce more notions. For any pair xy in a CGG, the length of xy, denoted by L of xy, is the length of the minimum path connecting x and y along the boundary of the convex hull. For example, in the CGG below, the length of x and y is 3 because the minimum length from x to y has length 3. And the length of x and j is 4 because the length of the minimum path from x to j along the boundary of the convex hull is 4. And in a complete CGG-Kn, the length of its edges range from 1 to n over 2. So for each length I that is strictly less than n over 2, there are n edges with length I. So the average length of edges of Kn is 1 plus little o1 times n over 4. Now, before showing you the general lemmas for non-packability. Let's try to prove it for some small examples. First, for the planar C5, for any copies of plane C5, the average length of its edges is at most n/5. Therefore, any C5 packing of Kn will cover edges of average length at most n/5. But we know that if there is an almost perfect C5 packing of Kn, then it will cover almost all edges of Kn. But we know that the average length of all edges of Kn is about n/4. So the average length of edges covered by this almost perfect C5 packing must have average length at least 1 minus little o1 times n/4. So it is at most n/5, but at the same time, at least n/4. So the fact that 1/5 less than 1/4 implies a contradiction. Now let's try to do a slightly more difficult example. That is a C5 with an extra chord. Let's call it C5 plus. For any C5 plus packing of Kn, the outer C5 will cover edges of average length at most n/5. And if there is an almost perfect C5 plus packing, then the outer C5 will cover 5/6 portion of almost all edges in Kn. Now let's consider the extremal case, that is, these edges are the shortest 5/6 portion of almost all edges of Kn. Then it contains almost all edges of length from 1 to n/2 times 5/6. This is because we know that the length of Kn range from 1 to n/2. So if it covered the shortest 5/6 portion of almost all edges, then it should cover all edges of length 1 to n/2 times 5/6, which is 5n/12. Therefore, its average length will be at least this 1 plus little o1 times 5n/24. So now we have it is at most n/5, but at least 5n/24. So the fact that 5/24 less than 1/5 will imply a contradiction. Okay, now based on this proof, we want to generalize this idea to a more general lemma. And before doing that, let me introduce more notion. Let G be a CGG. A set of edges of G is convex if for each edge EI, all other edges EJ lie on the same side of the line determined by EI. And if we look at the figures here, the set of blue edges is convex and the set of red edges is not, because the middle red edges will partition the plane into 2 parts and each part contains a red edge. Okay, here comes our general lemma. Let's call it the average length lemma, which illustrates what it is about. Let G be a CGG. If G is convex packable, then there exists some function f that maps each edge of G to some positive real number that satisfies the following 2 conditions. The first one is that for any set of edges S, the sum of f of E, while E ranges over all edges in S, is at least the size of S squared over 4 times E of G. And the second condition is for any convex set of edges A, the sum of f of E, while E ranges over A, is at most 1. The intuition of this function f is that basically it means if there is a perfect packing of G, this F will map the edge, map any edge E to the average length of all edges being covered by this edge E, divided by N. Okay, to convince you that this is true, let's try to use it to prove the non-packability of C5 and C5 plus again. For C5, if we assume it is convex packable, then we have this guaranteed function, and we consider the sum of f of E over all the edges of C5. Then by condition 1, we know that this sum is at least 25 over 20. And by condition 2, this sum is at most 1. So this 25 over 20 less or equal than 1 implies a contradiction. And for C5 plus, again, we consider the sum of f over the edges on the outer 5 cycle. Now the first condition says that this sum will be at least 25 over 24 because size of S is 5 and number of edges is 6. And the second condition tells us that this sum is at least 1. So now 25 over 24 less or equal than 1 implies a contradiction. Okay, now let's prove a more general proposition by lemma, the average length lemma. Let G be a CGG and let K be the maximum size of a convex set of edges of G if the number of edges in G is less than K squared over 4, then G is not convex packable. The proof is, suppose G is convex packable, and we let A be a convex set of edges of size K, then the two conditions and in lemma 4 gives the sum of f of E where E ranges over A is at least K squared over 4 times E of G, and at most 1. And simplifying this will give us the number of edges of G is at least K squared over 4, which contradicts our conditions. Okay, this is the proof, and we are going to use, and in fact, this proposition alone will prove the non-packability of almost all plane Hamiltonian CGGs. First, if G is a convex packable plane Hamiltonian CGG, then it is formed by adding T cos to CK. In fact, this is true only if G is plane Hamiltonian CGG. Okay, anyway, when K equals 5, by this proposition, we know that the number of edges of G is at least 7, which means that T is at least 2. So it has at least 2 chords. And when K equals 6, this proposition tells us that it has at least 3 chords. And when K is at least 7, we know that G must have strictly more than 2K minus 3 chords, which contradicts the planarity of G. Okay, so by this proposition, now the only remaining candidates for a convex packable plane Hamiltonian CGG are the plane cycles C3, C4, and the 5 CGGs in the figure below. So now we have 7 candidates left. So what remains to be done is to show that theta 5, the theta 5 here, is not convex packable. And we can do that by applications of lemma 4. What we do is we partition the edges of theta 5 into two sets, two convex sets. Then recall the two conditions from lemma 4. By the first condition, since these edges, they are all disjoint, by the first conditions, we know that it is at least 9 squared over 4 times 9. So it is 81 over 36. And by the second conditions, we know that it is at least 2, at most 2. So we have 81 over 36 is at most 2, which is a contradiction. So we complete the proof that theta 5 is not convex packable. Okay, so this completes the proof of the negative part of theorem 1. It seems I go faster than I expected. I have a page of open problems. So the main problem is that, can we show that P of G is geometric packable when G is one of theta 2, theta 3, and theta 4? And another problem is that this average length lemma, in fact, give us a necessary conditions for a CGG to be convex packable. And it is currently our only tool to prove that CGG is not convex packable. We are skeptical about whether it is also sufficient. In fact, I don't quite believe that it is sufficient. So it would be enlightening to discover an example that fails to satisfy the hypothesis of this average length lemma, but is still not convex packable. Okay, these are all I prepared to talk today. Any
Can
question?
you explain why you don't think that it is an if and only if condition?
Why I don't believe that it is sufficient?
Mm-hmm.
I don't know how. I just kind of feel it is not enough.
Because I remember that when I
Yeah.
still was part of the discussions about these questions, then at some point, I think you said, or some other people said, that they believe that this should be a sufficient condition, but maybe things happen since that I am not aware of.
The reason is that if we consider a caterpillar like this, very long caterpillar, and each vertex with one pendant edges, I kind of feel like this should not be packable. But if we have enough pendant edges on the endpoints, I mean, all the inner vertex have only one pendant edge. And if we have enough pendant edges on both endpoints, then it would satisfy the hypothesis of the average length lemma. But for some reason, I feel like that this should be unpackable for some other reasons. This is because if you imagine these caterpillars in a convex graph, then let me change the color. These edges, it should be large. These edges in the middle should be large, which means that the edges here should be small. And we have many long edges in the middle. And basically, these edges, it should be very small. I feel like we should be out of short edges. But yeah, so that's why I think it is not sufficient, but I did not did not show it yet.
Okay, thanks. So I think we should first thank Jiaxi for this nice talk. Are there any questions?
I have kind of two, if no one else does. Okay, first question. So everything you get out of Wilson says that you can cover all but linearly many edges, right? It's not just subquadratic, it's up to, I only miss linearly many for silly reasons. One of your examples with like a C4 with an extra edge, you're covering all but n log n. Is there a reason to believe that you can't cover all but linear? Like, is that log n, n log n actually important?
I didn't think too much on this, but
Fair enough.
yeah, that would be a good question to ask. Yeah, but I don't know the answer now.
Yeah. So, because you proved with C4 with an extra edge that you cover all but n log n, right? But then C4 by itself, you proved you covered all but linear, correct?
Yes.
Okay. Yeah.
Yeah.
Okay. Anyway, I mean, I understand why the log is inherent in your proof because of how you do it inductively. I'm just curious if it's actually important, like necessary.
Yeah.
And I guess second, oh, sorry.
We can show that for the CGG, we can cover everything but linear of them.
Okay.
This is unclear for complete graph in general position.
Fair enough. Sorry, complete graph in general position, you can do all but linear? What? Sorry?
For
all of these graphs are in general position, right?
For complete graph in convex position, we can it can be pegged. All but linear of them can be pegged. But in general position, we don't know.
I see. Sorry, I just misunderstood your statement. Okay, cool. And second question. You're restricting to Hamiltonian graphs is just a bit of a cop-out to be able to go to the convex position ones, right? Or is there like actually a reason to care about these ones more?
No.
Yeah, it's just to make your proofs go, right? I mean, I'm not missing something that's silly if I don't have a Hamilton cycle.
We haven't think too much on that. That's because we just try to find some family of graphs that is easier to approach. Yeah, the next step for us maybe to consider some other graph.
Okay, so it was actually just because of your approach and not that I'm missing something dumb about graphs without Hamilton cycles.
Yeah, it's just we haven't about it.
Just making sure. Oh, Bernard asks in chat, like, do you have some results for non-Hamiltonian graphs? It's Bernard's question.
In fact, we have some for CGG, the average length lemma, it is not restricted to Hamiltonian graphs. It is a general lemma for all CGG. And for geometric graphs, we have not seen too much yet. Yeah.
All right.
One small thing we can show is that the union of two triangles is geometric peggable. Let me take the whiteboard. This is geometric peggable. Somehow we can show this is geometric peggable. So it is quite similar to our theta 2. So, but it doesn't seem to help us to prove that theta 2 is geometry peggable. Yeah, this is what we have so far. This is good. This is, don't know.
But you also have results about caterpillars and other type of graphs, right?
Yeah, we have results on caterpillars about, but it's only about CGG.
Mhm.
So
And also like general graphs with like, when you add to those special type of graphs some chords on like some edges that go, like free edges that go from the vertices, you have some results about those too, right?
yeah, but yeah, those are also only for
Only for
convex.
CGG, yes.
Only for convex.
Mhm. Is it published already, or at least in archive?
No. We are planning to do that, but it took longer than we expected. But it will be submitted soon, maybe in a week or two. Yeah.
Yeah, this is very nice. It really developed since I last joined your meetings, so this is very nice.
Thank you.
Any other? Bernard is saying better convex than nothing in the chat, which is always true. Any other questions? Okay, if not, then let us thank Jieshi again for a nice talk. All right, so bye-bye.